All right. So let's get started here. We're back for another episode of the PE COFF generator project. And as usual, here's your reminder at the beginning that this project and all my other projects are funded by people who think that what I'm doing is cool and can afford to pitch in once or on a monthly or yearly basis. And you can do that by going to mrforth.com/membership. You can check out the perks. You can check out the supporter and membership options that we've got. But with that, let's get into the project. So today I'm going to go for some chill stuff. We've been working on a big API change, and now we're at the stage of the API work where the new API is in place. Everything we kind of thought about that might improve stuff has been done. The refactoring is working, so we're past all of that. And it's time to build new stuff using the new system and see what the iteration is like, right? So an API is like a surface. It's like a new terrain. And now we're going to go and explore that terrain and see if iterating on top of that feels good or bad. And that is the question that's always a little hard to predict ahead of time. The only way to really know is to do it. Okay. Let's start with imports. So for imports, the difference between imports and exports is exports creates a table that can be used for any purpose. We can use an export at runtime to load in a DLL and grab a procedure out of it, right? That's what my test load gen does. Grabs generated DLL, grabs the operate function, calls it. Imports are different. Imports have to happen automatically when the binary gets loaded. So in this case, what I think we need to do is we need to start by looking at what the structure of imports looks like and build that out. And then we also need to figure out what the test case is going to look like. And I think it'll be easier to think of a test case once we have looked at the structure of the imports. So let's do those steps first. Once we've done step 1, build the API for structuring and constructing imports. And step 2, set up a test case for imports. Then we'll finally get to actually do the part where we build the serializer for imports, and then we'll be testing the API we've been working on. These first few steps are kind of preliminary stuff we have to do for this new import structure. Now, let's put on some music. It's just for me. Play your own music. I am playing lo-fi today. All right. So pe.h import table. So my dumper already has this. It looks like Okay. So to take some notes, it looks like an import directory table is going to consist of import lookup table and a timestamp and we don't know what first forwarder index is about, actually. So, like, just default that to 0, I guess. A name. Turn my music down, it's too loud. And the IAT. So this part here, sorry if you can hear all the noise in the background. The IAT is going to be a little bit annoying and separately has to get built. The IAT is another space. It's kind of just a copy of the import lookup table, but it has to be copied separately and pointed at by the IAT here. If you look at my dump from the run, we'll see that the IAT is right here. And, you know, they're both part of our data, I believe. But anyway. So the import lookup table itself is like an array or a list of these things, which are our name and hint. Right? Now that's not the layout in memory, that's just the main information structure that we're dealing with here. Okay. Now, I think that a big difference here is that we can have more than one import table, right? Okay. Right. So there are multiple of these. Timestamp. Forwarder. Yeah, I don't know what this part means. We're gonna just... Yeah, we're just gonna default that to 0 and not fill it in. Hey there, Tool. The rewrite went well. It got, like, yesterday we got to the end and it was working. That was about where we ended. So today is testing out the new API by building something new with it. So we're working on load time imports now. Okay. So I think there's our API, or there's our construction data structure at least. The API for it is pretty rote. I don't know, how many of the people who are watching here are like beginners, intermediate, how much people are learning versus just hanging out. But I do hope, this is something I don't see a lot of people have a lot of confidence in. And I do hope people can see just how easy it is to like whip up a new data structure and start using it for something and see if you get the basics down of like writing chains and writing these little APIs. Like, I don't know how to highlight it because it's not that big a deal. It's not interesting, but you can just do it. You can just go. You can just start formatting your data in very simple ways with an API and then use it to construct all kinds of stuff, right? And I don't know if, I feel like I see a lot of people program it a way that doesn't show that they have a lot of confidence in doing something like this. And it's really worth getting comfortable with it. It's very, It's very convenient once you do. All right. In this case, we want to be able to create one of these lists, and then we want to be able to create tables on the list. Tables need a timestamp and a name. And then we want to be able to create imports, and that's it. Like, that's the whole imports table. And then finally we need the baker, which takes in, this is the thing that uses the new API now. It takes in our imports, and it should just create a new block. All right, let's see if that works. Right? Let me just keep, I'm just gonna keep trying to highlight this, even though I don't know how to highlight it yet. So like, all I've done to get started here is I figured out what the key information is that I need to specify from my software to fill in one of these tables that I'm serializing. And I just made a system of like linked list type data structures that I can declare very easily with like these construction code, right? So the generator context carries an arena around, and I just throw everything onto that. I link them up with linked lists like this. SLQ push list first, list I think that's first table, last table result. We increment our counter. So now our list contains our new thing. We want the result to contain the timestamp and the name. For now, I'm not copying the name. That could be a mistake. Question from Tool: how do you structure your arenas usually? Do you use just a solid block and pure linear allocation, or do you ever use a chunked one with reallocation and a free list? I don't use, like, neither of those describe what I do. I don't use a single pure linear block. I have a growing chain of blocks, but I don't do any reallocation or free lists either. I mean, I do free lists explicitly outside of the arena system, but my arenas itself aren't built with memory reclaiming strategies. So if you allocate something, and then you allocate, if you allocate, you allocate A, then you allocate B, and then you want a free A but keep B, then you're stuck. I don't give you a way to free A and then recycle that memory. You have to pop things in order. but I don't have limits. Like if I, we can take a quick look at what my arena looks like since you're asking. If we do arena alloc, you can see it initially creates this block. So it's like, where is it? Mem reserve size. That reserve size defaults to mem default reserve size. Where is that? Well, base.h, mem default reserve size, so gigabyte. I reserve a gigabyte, right? And that's usually enough. But if you were to allocate so much that it wasn't enough on the same, all on one arena, there is this possibility of reserving a new block. And then there's this chaining strategy. So if I were to drop my default memory, or if I were to allocate an arena with 1 megabyte and push it to its limit or something, we would start to see this more often. But my arena, once I create the arena, I can always use the same pointer. The head of the chain remains the same, but the head of the chain has a pointer to the end of the chain, and that's called current. And then each thing in the chain points back up the chain. So like the first one sits, like say here's my first arena block, and then I create a second arena block that has a pointer to prev, the previous arena block, and each new arena points back. So this chain grows and grows. The original point on the chain remains the handle that I use to access the arena, but it has a pointer to the end so that I can skip to the end of my stack of blocks basically with one extra indirection. So whenever the arena runs out, I just go, oh, okay, we need a new gigabyte block, reserve, commit the first 64 megs or whatever, and set up the handle to point at that and chain back. And then when I pop, if I happen to pop multiple blocks, I catch them all. Now, you'll notice that since my default is a gigabyte, this basically never happens in any of the code I'm actually running. But if I ever am in a situation where where I write a program that would process, say we're processing a PDB. In the modern world with programs like Chrome, PDBs are starting to get over 4 gigabytes. So now all of a sudden you're like, oh, 4 gigabytes, like, are we going to load that all into memory at once? Are we going to process that on an arena with a 1 gigabyte max? We don't have to, because we can just grow the arena. But yeah, 1 gigabyte, usually more than enough for everything anyway. Yeah, I really need to get out some videos about how I implement arenas, because I think people don't realize the breadth of options there are for maintaining the arena API with a performant implementation that has a lot of the restrictions removed from the default linear block. Yep, and the thing I described is in my code, so check this out. If you want to see what I'm talking about with code that already works, where is it? Here we go. You just pop over to mrforth.com, you go over to software, codebase, the code, source, base, alright, where did I put this? This code here is poorly organized. The new one is just, it's all in Mr. Forth base. That isn't out yet, so that's still an in-progress project. But if you go to, I think, small functions, okay, basic types, no, base types, arena. There's your arena. You can see the arena structure in base types.h, and then arena, no, okay, is it in big functions? Arena push, yeah, then you come down here, you read arena push, no zero, you read arena alloc reserve, and you will get the full picture. All right, this is the spicy part that we will do last, where we use the new block API to serialize, to capture the serialization of the imports. So that's using the new API to put exports and imports together into our data very easily. I hope that that works. All right, that still works. So that makes me think that the combining of the blocks worked at least, which is interesting. It feels like that should have failed. Yeah, it definitely should have failed to run. Right here it should have asserted because I gave it a null block pointer. Okay. Yeah, that's what should have happened. So why did that not happen? Oh. Run, fly. There we go. Okay, cool question. I'm new here. What is the PE COFF generation stuff for? I'm glad you asked. The PE COFF generator is a research project. I am gathering up as much information as I can about the PE COFF formats so that I can synthesize it into a series of other projects. But right now, this project is mostly for my own learning and gathering of information. So the things I want to be able to do are, one, I'd like to be able to describe the key ideas that we actually depend on. Not all the, there's plenty of stuff that's sort of our legacy that's in there, and I want to pull out and synthesize just the stuff we actually are relying on now, and make either a write-up or a video essay or something to package up that information and get it out there. Two, I want to make it possible to iterate on tools that generate and I want to make it possible to iterate on tools that generate executables more easily. Right now, we just rely on compiler and linker developers to sort of build the tool chain, and the stuff that creates our programs is baked in as half of those programs, right? On the type of input those programs have is a text file or an object file, and the type of output they have is an object file or an executable. And so that's the only interface we have for constructing software. And I would like to create some kind of library or set of tooling, like a executable diagnostics program that we can drop in an exe and that you generated yourself, and have it say like, oh, this is why your program isn't working. Here's where there are oddities about your program or whatever. Like, here's a visualization of what you've got so far and what is and isn't right. And I'd also like to have maybe a library or something like that for letting people get started making their own executable generators as easily as possible to open up the door to iterate on other types of software construction interfaces. So like once that stuff's out there, then the next steps might be to go and explore other forms of like new ideas about what the object files should look like, or what the executable should look like, or what interfaces we want. But right now I'm just feeling like we need to shore up all this arcane knowledge that has been lost about how to use this and get it out there for to make it quicker to iterate. Okay. So let's stop for a minute and talk about this. So this is an API issue, and that's what we're working on today. So let's talk about options we have. First of all, when I am constructing something new, like block from imports, right? So I started a new function. I have a default here just of like wanting to be able to return something. Now it could be a null, like I'm doing, a null block. It could also be that I want something like PEGen block nil, right? I might just want to have a global nil block. Now, the difference between these two is this is not a null pointer, and so you can access off of the block, right? You can go block child count, you can go block data, whatever. But you can't write. You can only read, right? I would mark it as read-only, so if someone were to do total size equals size or whatever, this would be error at runtime. Whereas if you wanted to do block total size, this would be okay, right? This would be if I use the nil thing. So this is where it's different from a null pointer, which is that it's safe to read off of it. And the problem then is that if I look at something like block push block, in this case, it's still necessary for the block right here to be checked. I would still have to go, hey, if block does not equal PEGen block nil, because as long as one of these is a nil, it can't be modified anyways, and both of them have to be modified in order to attach this block as a child onto this list. So, one way or the other, I think this function requires null checks. If either of these is null, we just don't do anything. And I'm going to assume that the first one here, the one that's being intentionally modified, is always going to be null. So we'll just have like, these are this type of function. But this is not. We'll say list should never be null, but block can be null. If list is null, then something worse is happening. But we can allow for the case of pass through to just work when block is null. Here we can do if block does not equal 0, result equals block total size. This is one that would just work automatically if we use a nil instead of a null. Similarly here, we wouldn't need a null check. Okay. But let's go with that. We'll do null checks for now. Okay, so everything is working. And now what's happening is when we do block, push, block, if this is if our data, well, not our data block, if imports block is being returned as a null, that's the same thing as an empty block right now, and so just nothing happens. Actually, that's a good point. If our block has a total size of 0, then we don't need to do anything. Right? That's not quite true. We still want to mark it as attached. The thing is we want to be able to say once you've attached something onto a list, you're not going to modify it anymore. But I guess we'll just stick empty blocks on because there is a danger that we might want to use the block as a label. And so we still need it to fit into the system in the same way for every other purpose. So I guess it's just, yeah, for now let's not try to optimize that out. Okay. So I think we've set everything up except for our test case. So we have importable.dll needs to get generated. Let's see. Importable, let's see. Test importable.c. I don't know, I just need like decal spec export or something like that. What is it called? Base.h runtime sim runtime decal spec DLL export extern c. Whoops, what are we what keyboard are we on here? Extern c decal spec DLL export int helper, right? That's the name of our function. Takes in x, and we'll have it calculate something like that, something interesting, doesn't matter. DLD unit root path testing test importable.c importable -- DLL. I guess in a C function you don't actually, in a C file you don't actually need extern C. That's a C++ thing. All right, so we generate importable DLL, I believe. Here. Importable DLL. And that should be exporting the helper function. So now the question is, can we call the helper function? Do we know how we would do that? Well, let's start with this. Mini asm call let's see, what is the syntax here? Godbolt, you might know. See, you don't know how to compile it? There we go. Ha 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 ha. I see. All right. Alright, so this isn't going to help. Alright, let's see if we can build Miniasm. Okay, I need to figure out how to tell it that helper is a DLL import. This might be a linker option kind of thing. No, not you. I need linker options. Hmm. Yeah, okay. It's not going to be here. It doesn't have anything about this. Where are we at here? Directives. Okay, cool. Where did assembler reference MASM? Okay, so if I was hanging out over here, directives reference, symbols reference, operators reference. Got it. Okay, cool. Okay, let's try this. Okay, so I guess D word or Q word maybe, because it's a 64-bit compilation. Okay, so now we've got a linker error. That's a lot better. Now we go back to our linker. No, it's not the symbol table that I want. Okay. I think if I remember correctly, the trick here is to just do something like importable.dll, maybe? What about importable.lib? Do we have one of those? Yeah, that's probably it. There we go. Okay. And then if I were to run mini exe, interesting. Let's take a look. So that's some garbage, right? Okay. What's going on there? Probably mini exe is not getting rebuilt. Okay, so library load success. Operate. Okay, something else is failing. So library load is successful. Pull out the operate function, and that succeeds. So then we go to call operate, and that goes fine, fine. And we call rip plus 4. Got it. So it generated this. Do you see this? This must be the plus 4. There must be 4 bytes. Yep, 4 bytes right there. So now let's run down to here, step into operate. When it does this call instruction and I F11, my debugger loses track of what's going on. I don't know where I am now. Weird. Okay, let's try this again. Call. Yeah, we lose track of our rip somehow. It should just be landing right here. But I don't see it. Where did rip actually go? Somewhere crazy. Okay. Here we go. Rip is at 77F. E6, and so on and so on. Its next address is supposed to be this. Plus 4. Which would be the same as this. Under ideal circumstances. And just out of curiosity, what do I find if I go to show me the bytes? 1, 2, 3, 4, 5, 6. Okay, so that's 6 more. So starting from here, plus 6, plus OXFE5. Come on. I wish I could copy paste that, but anyway. So that's where it's supposed to go next. When I F11 right here, my rip ends up here. That doesn't make any sense to me. Maybe I'm misinterpreting this. Maybe this says call keyword putter. It's actually a dereference. There it is. 1, 2, 3, 4. Yeah, look at that. So my rip. Oh, you don't know how to do the rip register? That's weird. Okay. You don't know how to copy paste that text. That's weird. F E 525FF. Right? Well, that's FF at the low byte, 25 at the next byte, E5 at the next byte, and 0F at the next byte. Yeah. So what's happening is this is not calling the right thing. It should be calling... this should be causing us to jump here, and then I presume that jump takes us to the DLL that we imported, but it didn't link it up right. It generated this, which is loading the jump instruction itself, and then we're getting garbage. The only other possibility, I think that that's the correct interpretation. It's supposed to be taking us here and then jumping ahead. The only other possibility I can think of is that maybe no, that's just garbage. Okay. Come on. Proto. Maybe that's what I need. Okay, hold on a sec. Still no good. See what happens now. If I F5 to here, I step in. Oh, so this is different. So that's progress. 7FFBE6D21014. So we're calling that. I like that. Now we have debug info, which is nice. We come out here, and EAX contains 13. If that's good, that's what it contains. We're going to return that. We add 1, we got 14 there. We're trying to return our call stack appears to be wrecked. Right, I don't have a good call stack anymore. I'm gonna go talk to Felix real quick. Remind me exactly how the ret instruction works, please. There you are. Okay, so you do know about RSP. Let's take RSP minus 8 and look at the next 8 bytes. We should see a pointer there. That could be a pointer. Let's look at it as a pointer now. Or as a... Okay. Like this. Yeah. Oh. That's the return to this. Huh. Okay, our call stack here looks fine. I call. Okay. So my call stack currently contains this at the top. And my RSP value itself, let's do this. So RSP is this. You come on. Let's go. There we go. So that's where our pointer was at. Then we go boom, boom. Now this call happens here. And for reasons I don't entirely understand, looks like we moved RSP up, we did some work, we put RSP back. Then we return. So it's right back where it started. But this has been modified. set up EAX, we call RSP gets modified once by this. By the way, the top of our stack so right here, the top of our stack is pointing at this value, which is where we want to return to. And there's the top of our stack. When I call this, it increments the stack by one pointer. Decrements it by one pointer, I should say. And look at this. It does do something. dword putter RSP plus 8. So I think what's going wrong is that I am making this call without doing some kind of necessary ABI stuff. But okay. All right, I can't figure it out that way. Let's figure it out this way. Come in here. Again, this is where we should be returning. This is where our stack is. We decrement the stack by one when we do the call. And then this is taking the liberty of moving ECX into RSP plus 8. And that's significant because RSP plus 8 is where that original stack pointer is supposed to be. Right? If I do... Wait a minute. No, hold on. I gotta do this a little differently. This is not the right spot to look. This is the right spot to look. Step in there. Boom, boom. Okay. BB1F 108. Again. Okay, so that right there, BB1F108 is the return after this. BB1F108 is the return after this. Okay. So this is where we should be returning to, and this is where our stack is starting. Whoops. Good. When I step in here, my stack pointer decrements by 1. And then this spot, which is RSP plus 8, which contains that critical information, gets modified by this. Right? So yeah. I think these are like this in this syntax. There we go. There we go. So I step in again. Now, X starts off as 7. We shift it up by 1. And then we XOR that with 3. And ultimately we have 13 in the RAX. We add 1, making it 14. Subtract the rest of that stack that we set up at the beginning, and we return. X comes out with a 14. Okay. Now, there we go. That's more like what I was looking for. Yeah, cool. Okay. Okay. So that took some doing, but now I have the ability, if I pop over here, I don't have it up yet. Imhex. Mini DLL now contains the starting point that I need. And the other thing I need is for the test case to go back to running the generated DLL. And now we are done building the test case and the example case, the sample version, to compare again. So let's go back to building our tools, run our generator, build. So this is still running just the old operate that we wrote right here. The new one starts right here. So there's return 1. And here is our new bytecode. So we got to figure these out piece by piece. Oh. Okay, so there's our ret. Right. Now our sub. Maybe the easy way to figure all this out would be to jump in right here. Oops. Okay, because I'm not done with mini just yet. Show code bytes. Okay. So 48 to 20 is our sub. Zero F to C9. So our IML ECX. E808000 is our call. How do you do that? FFB E5A. We're going to have to investigate that. We're going to do this as our call helper. Add is the next 3 bytes. Add EAX1. 48 through 20 is our add RSP OX20. Return. Jump. Keyword putter. Rip plus OX FE0. Okay. Now this part right here, I think that this must be a relative call. It is like saying 8 bytes basically, right? So 1, 2, 3, 4, 5, 6, 7, 8 lands us right there on that jump. Now that jump is a rip relative that says FE0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Zero, zero. 31, 32. Okay, it's not 4 bytes, it's 8 bytes. It's not 2 bytes, it's 4 bytes. And that ends us at 32, which is the amount you have to add to this to find 4K, so that this is a 4K jump over. Now, I'm going to guess if we were to dump mini, that we will discover we also need so mini itself has an import table and an export table, but I'm more curious about it doesn't have base relocations. Interesting. Okay, so this must be... Okay. Here's text, here's our data. It has a VOF of OX2000. That's the same VOF as the IAT. So this jump here is not a jump into the main function. If we were able to step through that properly, what we would see is that that jump leads us to... Oh, wait, no, this is a jump. So it's reading the address off of RIP plus this much. That is a pointer. That is a RIP relative pointer to the IAT offset of the thing we're trying to call. Cool. Got it. Okay. So this is hard-coded relative to where the jump ended up. It is not relocated because it's relative to something that is tied in with it. This is relocated to point at the IAT. Nice. Okay, cool. so this is out. Operate is still at 6 bytes. Text block plus 28. This is relative addressing to the IAT. So we need a helper IA slot label gen IAT block 0. All right, so we're gonna have to build these blocks next to make this work. I think we've done everything else. So we've got the patch v relative. Oh, this isn't filled in yet. Patch list, helper jump, helper IA slot. So this spot here needs to point at this spot here with a 32-bit relative pointer. Wherever we put that IA slot, okay. Patch vrel32 label. Okay. So yeah, the big unfinished piece now is that we don't actually have an IAT block or an import block. So let's see about building those. The imports. All right. Yep, here we go. Import table. We push onto the block one of these for the table count. Okay. +1. Table directory count. Load count. All right, so that tells us how many to load. The last one in the list is a null. The rest get filled in. Here's where things get complicated, because I don't think I can build just one of these at a time. I have to build the IAT and the import directories together, but luckily we have a data structure for that, right? Now I can build these blocks in parallel and then piece them together later in a different order. So it's going to be possible. It's just I'm going to have to change the API a little bit that I'm building for baking this, because I was trying to just return a block, but I'm actually going to need, oh, let's see here. Yeah, in the case of imports, we're going to need a block for the IAT and a block for the directory table. Block from imports, we're going to have a single one. We're going to call this blocks from imports. So then those blocks get assembled like this and stuck on right here. Okay. Now, finally, this needs to look like this. And this. Now we're going to push the array of directories onto the directory table. And then for each directory, we need to be able to fill all of these. Lookup table voff, unknown, timestamp. That's just the table timestamp. First forwarder index, we default that to 0. Name voff. We need to be able to place that. And import address table voff. We need to be able to place that. Let's get ready to fill all that in. So the name is curious to me. Let's try to handle that first. Over here in the COFF header, optional header, directories, where we talk about, which one is it? The import table at position 1. We get 8, 5, 6. That's this right here, right? Doesn't quite work. It's in it's in virtual offset. So 2194, we got to do calculator mode. Two 2194. Now, what section has a voff? It's probably our data, right? 8192. So that's minus 2000. 194 plus 1536. 1940 794 in hex should be our file offset. 794. Nice. Lookup table RVA dot time date stamp forwarder chain DLL name RVA. So that's a pointer to importable .dll. Address table RVA 8192. So that's a pointer to the IAT, while this is a pointer to the lookup table 8640. Now the lookup table itself, let's see, after address table RVA, we get a null entry. So there's 1, 2, 3, 4, 5 nulls there. then it begins right here at a 64-bit aligned spot. We've got the ordinal flag. Tells us that this is a name table RVA, which points us to this 0 here and this name here. Finally, we find the importable DLL here. Okay, that's something different. So, ordinal name, DLL name. Now, 8192 itself begins at 1536 600. And here we are seeing another pointer, an ordinal flag, a null, characteristics. I believe that this is supposed to get replaced with the actual address when it is loaded. I believe that's the idea. That's why it's 8 bytes on this platform, even though it's only using 32 bits and not 64 bits. It still needs to be replaced by an 8-byte pattern later. Okay. So there's more. Okay. Cool. All right. So the next thing that happens is we look at one of these import tables and we see how many imports we have. Wait. First of all, do I have an example? Okay, that's just that. Okay, let's look at running a dump on this, or on this. Yeah, so we've got multiple of those. Let's look at this one. In the hex editor. Let's look at directories. Okay. So here's the voff that we care about. Now let's go track down a section that contains that. 135168 plus 60,000 gets us to 195. Yeah, so it contains that. So subtract this voff, add in the foff. 187 2DE18. Two DE18. Okay. So from here, I should be able to see, yeah, we got a bunch of these pointers with the ordinal flag thing. And then we get all these names, and we can see the DLLs get written after the function name. Time begin period, win DLL. Hint 38, get user, hint 134, get name, user environment, crypt acquire context, crypt release context, crypt gen random, advanced API 32 DLL, open clipboard, close clipboard, set clipboard data, empty clipboard, user 32 DLL. Okay, got it. So something else I want to see in there. Let's open up ImHex again. We can go back to looking at mini exe. Yes. Looking at our directories again. Oh, mini exe doesn't have what I need. It's mini DLL. Yes. Mini exe is out. Directory 8596 with 40 bytes. So let's take a look at that. I want to see. Well, hold on. 40 bytes. I know that there are 5. Yeah, there are 20 bytes in each directory. So that's okay. the next thing that has to happen is when we have one of these tables, we know we're going to fill this directory here. We need to set up right. Eight 640. This here's our, okay, there's our import address table. Here it is again. Our import address table starts with a pointer, but we don't get a count. I think they must end with nulls as well. Let's take a look here. The last entry is set to 0 to indicate the end of the table. Yeah, so these are null terminated. So what needs to happen is import lookup table gets pushed on it gets pushed onto the import lookup table block. Import lookup table block. We ask for import count plus one of these. So import count plus one of them. We get our lookup table. And okay, so this is going to be a patch. We're going to end up needing the patch list here. Patch voff 32. We're going to point from patch list. We're going to point from, so the patch position is this guy as a pointer. And we're trying to point to the new import lookup table. Right, so this is the import lookup table VOF. And we are assigning to it with a patch pointer like that. Similarly, import address table is going to be the same exact thing on the IAT block. And we're going to assign to it in the exact same way. We allocate our import tables, and now we're going to have to fill our import tables. And for that, we need to loop over the tables we've got. Okay. Now the values in these things are made up of two parts, a low 31 bits and a high 1 bit. This is a pointer to there. More specifically, a VOF. And so the deal is this. If the import binary name is not 0, right? If we have a binary name, no, not binary name. If the import's name is not 0, we do one thing. Otherwise, we do this other thing, right? This just means we go imp ordinal and 1 LLU 63. But if it's in this case, then we have to set them both using a patch pointer. So set this to equal blah, set this import address table to equal blah, and then the question is, where is our destination pointer? We gotta go build that. So the size of this piece here, it's a little bit funky to fill this in. They are specified over here. And they go to even boundaries. Okay. So we take our names block and we're going to push name and hint equals PEGen block push array gen block import names U8, and then it's the size of the name. Let's say 32 name size, name and hint size is going to be 2 plus the name size plus 1 aligned up to a multiple of 2. Name and hint size. Now, the first 2 bytes will be name and hint. They will be set by the ordinal. Then the next bytes are name and hint plus 2, set by the name itself. And the next bytes are imp name.size plus 2 equals 0, right? Just to be sure. So we fill that in, and then we use pointers. We use patches to point these two V-offs, these two 32-bit V-offs at the hint name. And since this is the case where we don't need to set the high bit, we don't need to do anything else. These will just be the right thing now. So that fills up our import tables. After we've done that, we need to write the binary name. You know, I could just not do this part and say that whenever we go to do this, we do block push a line, gen block import names 0 aligned to a boundary of 2. All right, now we push on to the block import names. The table binary name. And then this right here is a matter of assigning the name V off with a patch. I've hit one of those songs that I feel like is too short and I have to loop it for a few minutes whenever I hit it. Okay, hold on. That can't be right. Okay, thank goodness. I was about to say we didn't just get it working. That is crazy. It should be harder than that. There we go. All right. Okay. So we want to start looking at the difference between mini DLL and generated DLL. The difference, including the diff. So which byte is this? We have different COFF header pointers right off the bat. It's always frustrating. All right, let's go fix the COFF header real quick. Looks like generated is a little shorter. Next. Okay. There we go. Timestamp, don't care. What's this one? E2. These are linker versions, don't care. B, F, B, image base. Okay. So this looks like our import directory table spot. Let's take a look at the directories we have. So in our generated DLL, something is garbagey. Let's actually switch over to looking at the dump. There we go. this is the dump of generated DLL, right? Run dump. Oh, this is generated exe. Let's switch to this. Load project. I mean, that seems right. That seems right. Let's take a careful look here. Our data, here's my import table, import directory. Just take me straight there. What does that look like? Name table, RVA, okay. Freeform sections. Right, so there's our IAT. And a null. Here's the hint. Well, a hint of 0, but where's my string? You know what I'm saying? There should be a helper string right there. I don't see that. Is that... Oh, wait, no. That's the same as this. 3010. 'So how can that be right? That would be 16. That would be right here. If we look at my section headers, the R data section. Wait a minute, what? Data. Why are these section names empty? That's weird. They show up properly over here. Let me just make sure to rerun this. Okay. Section name R data, vert RVA 1228. Pointer to raw data. Eight bytes for that. Why is there a hint? Export flags, name export flags. Export. You don't know. Export time data stamp. Yeah, so this thinks it's pointing right here, and it shouldn't be thinking that. These pointers should be down here. So our RVAs for the Okay, I think it's probably a bug in the block system. And I'll give you my reasons why in a sec. Okay, so if you take a look, when we attach this here, it has an offset of 16 because the import lookup table has 16 bytes. So this has an offset of 16 from this block. Now this block ends up being inside our data block farther down, but somehow that offset of 16 is being added to the section offset by itself. Take a look. I'm going to start from right here. Okay, let's start by looking at import blocks. Directory table has a total size of 40. Two directories. The first one is the real one, the second one's the null one. Each one's 20. IAT of 16. Import data of 40. That's 16 for another import table plus some string data. And we can see that here as two children. The first child has a size of 16. The next child... Ooh, that's no good. First child, next sibling. There we go. This one has a total size of 24 and an offset within its parent of 16. Now, as I go to build up the R data block, these will start getting modified. So this is going to become attached with an offset of 0. Then we attach the exports. Next, the directory table is going to get attached, and it's going to have an offset within its parent of 88. Very good. And finally, import data is going to get attached, and it's got an offset of 128. Okay. Now, that's cool. That's good to know. Give me a copy of that value there. No, that was useless. Give me a copy of that value there. I don't want all of this. I just want this. There's our import data. This is a PEGen block, actually. Okay. And it has an offset of 128 within its parent. And it has two children. The second child has an offset of 16 within its parent. So 16 plus 128 gives us the total offset within the R data section, right? Now later, the time is going to come to apply patches. And one of these patches, at least, is going to have a patch position with the same block. I never found it. Okay, so that was a mistake. It's not the same block. Import data, give me a copy of the pointer. Now jump to there. It's not the patch position that we're looking at. It's the target position that we're looking at. One of these points into this block, but calculates its position, I think, the wrong way. What's going on? Okay, so our patches don't have a copy of the import block or something? let's take a look at it this way. Import block. We've got this pointer that we care about. Now I want to look at all of my patch list. There should be somewhere in the patch list that we are pointing at. Oh, it's not going to be import data that we're pointing at. It's going to be... Okay, here's the pointer we care about. Copy value. Nope. Try again. Copy value. Paste. What? Come on. Is that really the value? Here's import data last child 2206 FB40378. Copy value. Paste. There it is. Okay. This is the pointer we care about right now. Somewhere in our patch list, we expect to find a target position that looks like that. So let's go back to the apply patches loop. Patch target position block. Okay, let's do this a different way. Let's go and look at where those patches are first created. Because I think these ones right here are coming out wrong. So I want to see what happens. Right here, you're going to get a target position, and that gives you a block plus an offset. Great. So the target position pointer we got gives us this block. Weirdly, I don't like that. That doesn't seem right. Let's try this a little more slowly. Hint name size is 9, so we have the size of the name plus 3. Yep. We fill in the ordinal, which is 0. We fill in the actual name. Looking good. And then we go, okay, we want to point this thing here at this thing here. And in order to achieve that, let's take a quick look at the block import names. There's the pointer to the block import names. It's currently carrying its own data. Okay. So we would expect the import names block to be the one that comes back with this target position putter now. They're not the same block. This block creates the hint name pointer. We fill it, and then when we use it as a position, it's not the right block that comes back. How is that happening? Actually, that's longer than expected. Okay. .408. Okay. I think that doesn't work. Name table RVA. Hint helper. Okay, so this now points at this. You can see how this is now 9 instead of a 1, and this is a 9. So I think that did it. We were calculating our labels wrong. I'm going to need to do a deep think about what the rules are on the block API. I'm taking note of that with respect to the one past last bytes. Okay, still doesn't load properly. Interesting, the error is 193 right now. Let me go and look at what that error code means, actually. So we're looking at Win32 test load gen load. I think we're looking at load library. Error 193. Bad exe format, that's all we get. Okay, okay. Anchor version. This one right here. 150. That's the beginning of the RVAs. So let's rearrange. think we can do no data section, no data section, no data section, and no relock section right now. Why are we crashing? That's a little weird. Okay, it must be because our layout is not expecting just four sections, it's expecting 2. Okay, so it didn't fail to load the exe. Something else happened there. Let's have a look. Yes. Yes. Library load success. Operate comes back. We step into operate and we see all of this. Now this is a little different than what it looked like in mini DLL. Yeah. Okay. Boom, boom, boom. Here's where things are about to get tricky. Yeah, so that's still a call to right here. From here, we are looking at this address plus 6 plus FE4 lands us right there. That seems wrong, actually. Well, let's take a look. This should be a 64-bit address. And it looks like that. Doesn't seem great. What if it was this? Then it seems right. That seems like what it should be. So we have... Where's that V relative? Yeah. It's a little mistake. But we need to specify a bias here. There it is. All right. Okay. We step into our DLL. We just load a generated DLL. It calls into importable. It returns, and X is 98 as it's supposed to be. Rerun the diff here. Yeah, we don't have the P data that comes with the mini, so our size is a little smaller. Alright, well, this was just a kind of cool, groovy, we made progress. To review, I now can generate import tables. I also thought of a few other things that need to happen here along the way. So to review, we can now generate imports from a loosely structured constructor system. So I can just do import new, I can just kind of plop down the data however I receive it. And then I can turn it into a series of blocks and pointer patches that create the import. The block system itself was actually really helpful for this because it turns out with imports, we have all these different spots that we're trying to line up. We need to make a directory table, an import address table, an import lookup table. These two are supposed to sort of be the same thing in parallel, except that this one, but they need to be separate copies. This needs to point at this one. We need a pointer to this in the directory of the extended header. We need a pointer to this in the directory of the extended header. We need pointers from here to here and from here to here. And then we need to put all of that together in the right order in the R data section, along with everything else that goes in the R data section. And so these blocks are starting to actually really shine. If we had done this first, we would have broken our brains trying to do this on the section system. But now we can create these blocks and create pointers between them. Now, and it's just like, it's working really well. And we can rearrange the order of the data freely later without having to worry so much about it. And it's just great. Like, I really like how this API has simplified this particular problem. Seemed like a success to me. New things did come up. I think there's an issue to consider regarding how we think about offsets being valid within a block. If I have a block of 16 bytes and I take the offset of that block plus 16, is that a valid way to reference whatever comes after the block? And if I have a pointer to that thing, should that point into the block or not? Because right now I have an ambiguity where the pointer to the next byte could be allocated by a different block, right? If I have two blocks that both have data sitting in my memory, then the pointer to the first byte of the second block, right? If this is my second block and this is my first, and this is the first byte right here of the second block, a pointer to this is the same thing as a pointer to the end of this, right? One past the last on that. And so I don't know what should be the rule for one past last. I don't think we want to be able to index farther than that, but it might be very useful to be able to index one past last, and so we might have to think carefully about how that's going to work. There's also an issue of alignment. So right now, there is a thing here, which is that this is supposed to align to 8. This is supposed to align to 8. And they, especially the IAT, the IAT, well, both of these, this just gets plugged into another block. These two here get plugged into block import data with, this one's first, so it's got an align of 8 within that block, but then that gets plugged into the R data, which, has got a directory table and export. All of these have to happen to be aligning to 8 for now. But we need to be able to ensure that and make sure that it's automatic, so that if this, for instance, had a length of 4, a multiple of 4 in its length, which it could because the size of this is multiples of 20. So if I had 2 directory tables, if I had 2 DLLs to import, I'd end up with 60, which is not a multiple of 8, and then this would not be aligned, and then this would not be aligned, and so on and so on. So there is an alignment problem where a block needs to be able to know what its base alignment is, and it needs to not change as we aggregate them into larger blocks over time. So that needs to be dealt with. However, overall, even though new issues have come up about the API that need to be considered, I think this very much proved out the point. The import table was by far the most complicated thing to generate that I've done so far. We managed to do it today in a 3-hour stream, just on top of the system of blocks and rearranging things. So that's really cool. The offset system, the patching system, actually is working. There was a bug in the mapping because of that abutting blocks pointer question. That's where we got that bug where patching wasn't quite working automatically for freezies. But now that we know about the abutting address ranges problem, we're going to be able to think that through and do an even better job on that. The other thing that's a little wonky that I still need to get used to is these v-relative. The relative, I guess v-rel isn't even accurate. It's just relative 32, right? Well, it's still v-relative because it's relative within the virtual offset. But there's still this question of the bias here, and like this is a little bit hacky. It's not that hacky, but like the reason that we do this is because we are patching these 4 bytes, and the way that rep relative addressing works is that it's actually going to take the address from here, right? So at 4 later, right? This is the whole instruction, and when it does rip plus something, it's taking the value of rip after this instruction. But the thing we're patching is here. So we have this, like, the thing we're patching is 4 less than the thing we're actually doing relative from. And so we need to adjust for that when we're looking at where we actually think the relative address is based. It's based right here. So, but the patch is right here, so 4 off from it. The point is, there's no real magic way to make that automatic. What would have to happen is this would be handled if I knew, like, hey, I'm patching a jump instruction located here, that it has this particular layout. Then it could know, like, okay, so then the end of the jump instruction is here, the point we're patching here. Then it could start to automate this. Until then, we have to manually do this part. And that's fine. That's a layer for once you understand, once you're baking in information about what architecture you're targeting, then we could automate away this manually fixing the bias on our relative pointers. But until we are, but right now we're not building anything that is assuming x64. We're building all of the basic stuff for arranging this, and layers like an x64 assumption would be more specialized than I want to be. So we're going to keep hacking that. Feels a little funny, but I don't think that there's anything to do to make it better at the moment. Is there anything else that popped out at me? Really loved how that worked. I really loved how that worked. The patch list pointer is annoying to me. I had to go and pass that through at some point. I do think having the patches actually live as just a part of the blocks makes more sense, having them exist as a sub-data structure on the block. What's weird about that is that the apply patches thing feels off then. I think what needs to happen is that as we are building the layout, we are attaching blocks one by one, and there needs to be a part that's just like, hey, when you go to finalize, what happens is all the blocks you've attached finally get rendered out into flat arrays, and pointer patching applies all at once. I think that might be the right mental model for what's happening with blocks when we attach them to layouts and then finalize them. We have to keep in mind that applying patches isn't just a matter of blocks. It also depends on that virtual layout, right? Patches need to know what the virtual layout is to be applied. So even though they live on the blocks and they get applied when we go to finalize, we're actually kind of combining all those blocks together into a final layout, and then using the layout we've constructed plus the patches that we have hanging on the blocks to build the final version of the data. So it is a little bit special. There's like a special twist there I got to keep in mind, but I think that'll be better too. Overall, very good. I think the next big step is going to be to do this again tomorrow and try to do something like importing kernel 32 DLL, maybe trying to get C runtime working or something. Like I want to see if I can use the imports that I've got. I think we did this part. We do need to ask a question. I don't actually know why we didn't have unwind information in our research for the dumper already. All of this can go away. Let's just check this out real quick. Did we talk about pdata? Table entries that are used for exception handling. Oh, you call it exception handling. Right. But it's just right here. Here's unwind information. We just don't have any data on the unwind information sitting right here, but it's somewhere in there, right? If we did p data, we would get exceptions. We would also get unwind information. We have to figure out how that's encoded some other time. Let's go over to the dumper and leave a note. Dump.c. Boom. Okay, that's it for today. Let's check in. Binary PE, what did we do? We did generate load time import tables. Right quit. All right, and that'll be it. As a reminder, if you've been hanging out, I'm sure you might already know, but I'll just remind you that this whole project, I'm doing it hoping that people will be inspired and able to pitch in, $5 a month, $15 a month, or maybe on a yearly basis, and keep this stuff going. I've got a lot of plans for things we're going to work on, and I think things are really starting to roll in a good direction. So we'll be getting some projects out probably by the end of the year, but or early next year. But do consider pitching in if you can, because I am counting on anyone who appreciates this work to become a part of this. So consider that. And with that, I will sign off for the day. See you around the internet.